Hello everyone, my name is Sadali and you're watching Scientist Academy. So today I'm going to talk about Markovian and non-Markovian dynamics of trade-off behavior of quantum coherence and entanglement in extended cluster spin-half XY model under Dzyaloshinskii-Moriya interaction. So first of all, I would like to discuss some background about this problem, and then I will be discussing the calculations, how I diagonalized the Hamiltonian for this system and how we came up with the quantum state for the system. So recently there has been a huge interest in understanding quantum systems, particularly due to the discovery of entanglement sudden death, which is called ESD. The ESD is a phenomena in which the interaction between quantum systems and environment basically cause the entanglement between the system's component to disappear for a certain amount of time, and then it again appears in contrast to the usual decay pattern, right? So usually in some cases in quantum systems, when entanglement exponentially dies out and then it doesn't appears back to the system, then it's obviously the exponential decay, complete decay. But in contrast to this, in entanglement sudden death, it appears after a certain interval of time. When it disappears from the system, it comes back to the system. So the researchers nowadays has been trying to investigate the dynamics of this behavior of entanglement for two-qubit system and multi-party system interacting with the stochastic environment, and discovered that entanglement revivals are possible, right? So the dynamics of open quantum system can be classified as either Markovian and non-Markovian. Now I would like to explain what is Markovian dynamics and what is non-Markovian dynamics. So in Markovian dynamics, the information flow only occurs from system to surrounding or environment, and the system's correlation, which we usually quantify in terms of negativity or concurrence, decays exponentially and it dies down to zero, but do not appears in finite interval of time. It doesn't revive, means. So in Markovian dynamics, there is no such thing as entanglement sudden death, no revival basically. So however, in non-Markovian dynamics, information flow can be either from system to surrounding or environment, or environment to the system. So in soft matter physics and condensed matter physics, which involves strong correlation between the system and environment, are ideal for studying the non-Markovian dynamics, right? So while the system of study of open quantum systems initially focused on Markovian dynamics or Markov approximation, but recently the search has been explored for non-Markovian environment as well. So therefore, so various types of environment, including individual, independent, common, and combined situation, have been considered in quantum optics and even in condensed matter theory. So notably, a system in contact with non-Markovian dynamics exhibit entanglement revival, right? So as I said earlier, that in non-Markovian behavior can be seen in non-Markovian environments, the entanglement revival can be observed and has been observed even in theory and both in experiment. So it has been found that even in the limit of an infinite environment, non-Markovian effects are present due to the contribution of energy density, right? So the impact of quantum correlation within the quantum system, within the environment on the evolution of spin chain, has also been studied in the recent past. So the presence of entanglement in the environmental system accelerates the non-Markovian behavior of chains dynamics. So as you know, the entanglement is a resource, and we don't want to spoil our quantum resource, which usually flows from system to surrounding. So our desire is to get it back to the system from environment, and it occurs in non-Markovian dynamics, so in non-Markovian situations. So recent research indicates that environmental criticality significantly affect the information exchange between the system and the environment. So non-Markovianity as a measure of criticality plays a key role in this model. So first of all, in order to study this system, we need to understand what is fermionization approach. Fermionization approaches are the theoretical techniques used to describe the behavior of quantum systems, interaction of quantum systems or quantum particles in terms of non-interacting fermions, right? So the method provides a powerful tool to study the strongly correlated quantum systems, and widely used in condensed matter theory and in quantum many-body theory. So here are some of the fermionization approaches available in the literature as of now. So first one is Jordan-Wigner transformation, the second one is Bethe-Ansatz, third one is slab particle method, and the fourth one is density matrix renormalization group. So my understanding is in the first and the fourth technique. But right now I will be using the first technique, which is Jordan-Wigner transformation, which is a standard way of diagonalizing the many particles Hamiltonian, right? So I will be dealing with this method, first fermionization method. So first of all, I would like to discuss the fermionic algebra. I will not discuss it in detail, but yes, I will be outlining the key equations that are required to do fermionization algebra technique. So Jordan-Wigner transformation is a fermionization technique used to map spin systems onto the system of non-interacting fermions. Means you have a system which is described by the spin operators, and we translate that spin operator algebra into fermionic non-interacting fermionic creation and annihilation operator algebra. This is basically fermionization technique, and we are using Jordan-Wigner transformation method. So this method has application in condensed matter physics, quantum information theory, quantum computing, etc. So the transformation, as I said, allows us to express spin operators in terms of fermionic operators, non-interacting spinless fermion in particular, enabling the analysis of spin system in a fermionic language. So the first equation, as we know from standard algebra of quantum mechanics, is that the x component of a spin operator can be represented in terms of the sum of raising and lowering operator of spin yes, not creation and annihilation, but yes, ladder operators. So these are the ladder operators, and through ladder operators we can write the x component of spin algebra and y component of spin operator. So these two equations are key equations for our this transformation. So then when you have these two things in hand, then you can do Jordan-Wigner transformation, whose equations are outlined from 3 to 6, right? So here you can see Sn plus can be transformed into Cn dagger, Sn minus is transformed into Cn, Cn and Cn daggers are for spinless fermionic creation and annihilation operator, whereas Snz, z component of a spin operator, can be represented in terms of number operator in the number operator, which is Cn dagger Cn minus 1/2 times identity matrix. Similarly, if you have the product of two ladder operators in spin algebra, then you can transform it into creation and annihilation operator between nth spin and nth plus 1 spin. Right, so this is equation 6. So this is the set of equations from Jordan-Wigner transformation. So now this is the situation where we have one-dimensional spin chain, but here I have shown in the plane because I want to show that there are interaction between nearest neighbor and next nearest neighbor. So if this is the first spin, this is second, and this is third, then the interaction between two spin 1 and spin 2 is j, whereas spin 1 and spin 3 is j prime, right? So that is why they showed this one-dimensional spin chain in terms of two-dimensional configuration of spins. So it is just a one-dimensional Heisenberg model, not two-dimensional right now. So just because we are using Jordan-Wigner transformation, which translates our operators from a spin algebra to non-spin fermionic operators, which is creation and annihilation operator. So obviously, as you know, that fermions do obey Pauli's exclusion principle, and different spin operators, different creation and annihilation operator corresponding to different sites on the free lattice models can basically satisfy anti-commutation relation, which is equation 8, and similarly the anti-commutation of on different side of creation as well as annihilation operator is 0, right? So here I have just jot down the details of what is Pauli's exclusion principle and what is its role in the filling of spin states in fermionic in terms of fermionic operators. So now let's move on to the model. This is the model where the first term corresponds to Heisenberg XY model, where just because we have two terms, Snx and Sny, means the x component of spin is involved and y component of spin is involved, and there are n spins, capital N. And in future we will justify it in terms of thermodynamic limits. So as of now there are n spins, and so we will make some simplification when we say n goes to infinity, like in thermodynamic limit. Whereas the second term is the DM interaction, which is a spin-orbit coupling interaction between two nearest particles in two nearest spins in this one-dimensional XY model. Whereas if we consider that there are next nearest neighbor interaction as well, then we can write the further J prime interaction in between nth spin and nn plus 2 spin, which is the third term, whereas the fourth term corresponds to the DM interaction for next nearest neighbor. So this is D prime, J prime. So if you look at look carefully, then there are basically four major terms in this Hamiltonian, right? So now in order to simplify this model, first we need to set each term is another variable so that we can deal it one by one. So here h is equal to O plus P plus Q plus R, whereas O is defined in this way, the first term of Hamiltonian, P is the second term of Hamiltonian, Q is the third term of Hamiltonian, and R is the fourth term of Hamiltonian. Now we are going to recast these four equations. Equation 10, basically the Hamiltonian in terms of ladder operators. So we can do it by using the standard algebra of spin. So Nx can be written as Sn plus x, Sn plus Sn minus divided by 2, whereas Sny can be written as Sn plus minus Sny divided by 2 iota. So if we do that here, we simplify our Hamiltonian, first part of Hamiltonian, that is O, in terms of K ladder operator Sn plus and Sn minus. Now we will apply Jordan-Wigner transformation on Sn plus 1 minus, Sn minus, Sn plus, Sn n plus 1 into plus to the power to the superscript plus. So if we apply Jordan-Wigner transformation, we get this equation 16. Now you can see this equation is totally in terms of fermionic non-spin creation and annihilation operator for n plus 1 spin, right? Again, in the same spirit, if we do the same algebra for P, Q, and R, we get their corresponding Hamiltonian interaction, Hamiltonian for the major Hamiltonian that we wrote in equation 16. And so we are left with if we perform the same calculation for all the parts of Hamiltonian, we get this long it's not easy to describe each and everything over here. Just the algebra is very straightforward because I have written each and everything on this PDF file, so you can have a look at it. So in the end, so we get this equation for 24, which is the Hamiltonian for our system, and you can see that Cn dagger and Cn plus 1 are carrying G and D term. Cn dagger and Cn, obviously the Hermitian conjugate of the first term is second term. Similarly, for next nearest interaction in terms of JJ coupling, in terms of spin-spin coupling and the spin-orbit coupling, we get third and fourth term, whereas fourth term is the Hermitian conjugate of third term and vice versa. So now that we have the Hamiltonian in the form of creation and annihilation operators, fermionic operators, then now we can, and obviously this Hamiltonian is in position space. So what we do now is to transform it to in the momentum space just by doing discrete Fourier transform, so that we can diagonalize this Hamiltonian. And once we get the diagonalized Hamiltonian, then it's quite easy to get the eigenvalues or the energy spectrum of this Hamiltonian. Along with that, we can get obviously the eigenstates of this Hamiltonian. So what we do now is obviously the application of Fourier transform, discrete Fourier transform, in fact, where CKs are the momentum space, the creation and annihilation operator. CK dagger and CK are the creation and annihilation operator in momentum space, whereas Cn dagger and Cn are creation and annihilation operator in position space. So if we do this and applying some standard properties of Dirac delta notation, Dirac delta function, Kronecker delta function basically, and some contraction of indices, we come up with this Hamiltonian, right? So this is the Hamiltonian. So provided while assuming the fact that exponential iota k minus q times n is equal to summation over n from 1 to capital N exponential iota k minus q, both are equal, right? Both are symmetric functions. So it is equal to n times Kronecker delta function qk, where this equality becomes n when q is equal to k. So we will contract these indices by assuming that q is equal to k in the calculation. Then we will get the Hamiltonian in diagonalized form, right? So by the way, this condition is called consistency relation, right? So this is how we get our Hamiltonian. Yes, this is the Hamiltonian. So this is the Hamiltonian. If we simplify and use the identities, e to the power iota theta plus e to the power minus iota theta divided by 2 is equal to cos theta. Similarly, e to the power iota theta minus e to the power minus iota theta divided by 2 iota is obviously sine theta. So instead of writing theta, we have k and 2k, right? So the first equation number 13 is the diagonalized Hamiltonian. And why it is diagonalized, then you can see, for that you can see the summation is only 1 over here on k, and so ck dagger is times ck just shows that this Hamiltonian is diagonalized because there is no other summation involved except for k. And here is this ck dagger. Ck is obviously the number operator for kth site of this free Hamiltonian free lattice model, XY model. So here we let epsilon of k be, to be this long I energy spectrum, which is written over here. So once you get this, you can obviously write this Hamiltonian in a very compact form, which is equation 32. Now is the time to consider a situation. For example, this is one-dimensional spin chain, and by the way, we have shown this in the form of circular ring. Why? Because we are assuming one-dimensional spin chain, and we assume that the spins are basically very large in number, and there are the periodic boundary conditions, right, between the first and last spin. So if that is the case, then obviously we can write, we can just pictorially draw this one-dimensional spin chain in the form of ring. Right, and now we are assuming a situation where the two spins, let's say nth spin and nth plus 1 spin constitutes a system of two spins, then they are entangled with each other. And obviously if they are maximally entangled states, then we know from the entanglement monogamy theorem that if the two particles are maximally entangled, then there is no possibility for third or fourth or nth particle to be entangled with the system of two particles. So these two particles are entangled, then the rest of the chain is considered to be environment, and they are separable from the system. So by separable, I mean they are in product state with respect to the system. So system and environment are in the separable state, which can be represented like this, equation 33. Here at time t equals 0, the first system if we assume system, then since it is sharing an entangled state and Bell state, so if the first particle, nth particle, is in state 1, then n plus 1 is in state 2, with the probability 1 by square root of probability amplitude 1 by square root 2. Similarly, exponential iota theta phi is the relative phase, right? And so this is the thing. So, and similarly, the other possibility for an entangled state is that with either the second particle, first particle is in 0 state, whereas the second or nth plus 1 particle is in state 1. Multiply by the tensor product, which is multiply means this tensor product that shows just this is a product state, times the rest of the states of environment, and we assume that environment state are all in ground state. Right? So what would happen when the time goes on? Obviously, these two states Hamiltonian will basically governed by the Hamiltonian, and the state of two qubit system will be governed by the Hamiltonian, as which we just diagonalized. So which we can write it like this, right? So we can write it like this. Similarly, in equation 35. But before that, I would like to write this two qubit state equivalently in terms of annihilation creation operator, because see, we can write it like here it should be a 0 term over here, so cat 0 is here. So see, if we multiply Cn dagger with cat 0, right, where cat 0 is the cat 0 product of two qubits, okay, 0n and 0n plus 1. If the first creation operator applies on nth spin, then it will pop up one state, whereas the second will be 0 again. But whereas if we look at the second term over here, then Cn plus 1 dagger will pop up 0 from pop up 1 in the second state, whereas the first one will be obviously 0, and just because it is in superposition, so it creates a Bell state. So this is the state in terms of creation operator for n plus 1 spin site. So now that this state is given, so obviously the time evolution of this state at time 0 will give us psi of t. So that can be written in the form of unitary operator, unitary transformation, which is e to the power minus iota h t divided by h cross or h bar, that we have set to it to be set to be 1 for the sake of simplicity. So this is the thing now. So this is time evolved state, the state at any time t of the system, okay, with the governing Hamiltonian is shown earlier. So now again there is a compatibility issue, because the Hamiltonian is in momentum space, whereas Cn dagger and Cn plus 1, obviously n corresponds to the position site, n is the position, shows the position of the site. So we can transform this Cn dagger and Cn plus 1 dagger into momentum space, because we need compatibility in this equation 35. So if we do that in the same spirit as we did earlier as well, so equation 35, if we do it in 35 not 34, we get this thing, right? So there appears some exponential factors over here, okay. Then now that we have exponential to the power operator h, so we can apply the Taylor expansion, and there we get three indices q, q prime and k. So obviously the Hamiltonian is diagonalized, and we have some properties of creation and annihilation operator of fermions in the form of anti-commutation relation, that is equal to n times, if you know, n times the Kronecker delta function. So if we apply the same property over here as we did earlier in this calculation, we will get equation number 42, right? So this 42 is the Hamiltonian, and if we contract this and if we simplify this again, if we identify this equation over here, this thing, then obviously this is again the exponential, but now in this exponential there is no such thing as creation and annihilation operator like earlier in the initial unitary operator. So we get 43, equation 43. So if we substitute epsilon k that we defined earlier, which is the energy eigenspectrum, in 43 we get this finalized equation 44. This is the state of two spins on a one-dimensional extended Heisenberg XY model, where the two systems were initially entangled, but what would happen as time goes on will basically be determined from this equation number 44. So this is it for today. So I will come up with the further calculation of what would be the dynamics of quantum correlation and coherence in this system as time goes on, right? Since there are two J couplings, the first one is J and the second one is J prime, and we know from our earlier understanding that if J prime is greater than J, then this is non-Markovian behavior, and if J is greater than J prime, then this is Markovian behavior. So I will be dealing with these two situations, and not only that, but also I will be considering D and D prime. What would happen if D is greater than D prime, and vice versa? What would happen? So we will be looking at these issues later, but I will be starting from equation 44 because it is done as it is just derived. Now it is in front of us, so we can do this. So what would I be doing is I will generate the density matrix from equation 44, and then I will compute concurrence, first order coherence, and intrinsic concurrence, other major as well, and we'll try to look at the non-Markovian behavior while varying the values of J, J prime, D, D prime. So until next video, Allah Hafiz, and thanks for watching this video.